All right, so before we continue with sorting, let's now talk about reminders quickly. So your solution to assignment number 1 has been released on Tuesday. So take a look. So there are 2 parts for the solution. Part number 1, you can definitely look at the Java source code directly, study that, and reach out to me if you got any trouble understanding it or even reproducing something similar yourself. That's the most important lesson to learn, really. And then the second part is really a PDF document also on the eClass site. There are links to some tutorial videos which I kind of walk you through the solution line by line. If you really need it, you can also feel free to use it. Kind of optional, okay, for assignment number 1. I'll wait for you. If you need it, reach out to me. And the split array header, right? I'm not yet to release a solution. You guys really want to try. I really want you to be able to do it rather than just to see the solution directly, right? If that's what you're thinking, you better try first, okay? And also, this is something kind of new, but for those of you who might need it, okay? So if you go to the lecture site, I may not kind of remind you like every time. That might be too many emails you're going to receive from me. So if you look at the lecture site, so starting from today's lecture, you will see that for you guys, it's section Z over here. You will see this, usually it's an annotated version, which I'll post later, but you will see that before the class, I'll try to make it maybe 1 hour at least ahead of the lecture. If you click on that, so that will be the clean version of the notes, which I plan to use for the lecture. So if you want to print it out, or if you want to load it to your tablet computer, so easier for you to take notes, feel free. Okay, that one just for those of you who might need it. Okay. And as I said, I'll try to make it available maybe at least 1 hour ahead of the lecture. Okay. And office hour, TA contact, just the same as before. Any question about the course? Good. Let's do a recap before we continue with the sorting. So last time, we basically continue with the theme about applying the big O, the notion about asymptotic upper bounds into the context of Java coding, right? Just about algorithm in more general sense. Executable code, something that's executable. So we look at the various examples about given a piece of code written in Java syntax, how do you, number 1, derive the tightest asymptotic upper bound? Not just being correct, it's got to be the tightest, the most accurate asymptotic upper bound. That'll be step number 1. And step number 2, you're actually going to show the work justifying your answer, right? So we spoke about if you got, for example, nested loop or even a single loop, the essence of it is really to see the pattern of the loop counter and try to enumerate them and try to count all the steps together. Okay, so that's something you will have to pay attention to. So the first example we did is just about the first nested loop. You can definitely dive into the details about that one there. Okay, and let me know if you got any trouble understanding. And the variance of that is just to say, whenever you see double nested loop, it doesn't necessarily mean you will get quadratic algorithm. Not really. You really have to see exactly what's the bounds for each loop, outer loop and inner loop. For example, if I simply change the outer loop bound into some very large constant, it's just going to make the algorithm ultimately not quadratic, but just linear. Similarly, if I just change the bounds for the outer loop and inner loop to be also very large constant, it will just make the overall algorithm constant as well. So you really got to watch out about the bounds for the loop counter. That's really the key. And this one here, the main lesson here is to say the parts of your algorithm that has the most expensive running time is actually going to dominate. Right? So here you can see that n squared is going to dominate. So another way for you to guess quickly is to skim through the algorithm into different parts and see which part is going to have the highest power asymptotically. And that one's going to dominate. That's a very good way for you to guess first. And then, of course, if you want to justify, you got to show more work, right, to really get the credits. All right, so that's the last example here, slightly trickier. So you will see the loop pattern here. We still got nested loop. And then we got actually this guy over here, it's more like a triangle shape. Of course, one of your fellow students, very clever, they suggest you can simply calculate the area of the triangle. You will also get n squared. That's not a problem for this one. However, to really make it more general for you, you might have loop pattern that does not really boil down into a triangular shape. You might get something else. So I would say really try to focus on how exactly we count the number of iterations. right? That's especially the number of combinations of the two loop counters. And interestingly, we'll see another instance of like this today in one of the sorting algorithm. All right, we'll get there. So make sure you review the details of this and make sure you understand that. And as I said, later on, when we get a little bit closer to your written test number 1 later, I'll give you guys some example like this. Still given some very similar piece of code. Rather than approximating the asymptotic upper bound, what about I ask you to count the number of precise primitive operation? So that will require even more caution about how you kind of figure out exactly the values, right? I'll get there. Okay, we'll also go over the solution later. All right, and we talk about you also need an arithmetic sequence formula, right? It's basically n squared, but for those of you who might be wondering about what arithmetic sequence might be, you gotta brush up on that. And later on, when we talk about trees after the reading week, you will also need another sequence, geometrical sequence. That's something we'll get into later, not for now. And that's basically, okay, so up to here, that's the lecture for asymptotic analysis, okay? And then we move on to the new lecture about arrays versus linked list. Today, hopefully we can dive into linked list at least for some introduction, okay? Because your assignment number 2 is gonna be released on schedule sometime next week. We'll see how the lecture goes. We can slightly delay, okay? So we can give you a little bit more time to complete the assignments. So this is the first example we went through. So this is a typical scenario where it is expensive to perform such operation into the array. So we are trying to, let's say, given this input array here, you got some elements there already. Somehow you want to insert into the middle. Briefly speaking, this element here can remain the same. However, somehow in order to insert new elements, you have to shift everything there to the right by 1 position. In order to do that shift systematically, you need a loop. And in the worst case, that loop is going to run the number of iterations corresponding to the size of the array. That's the worst case. All right, so that's something you got to remember. You guys can just go over the detail about, let's say, number 1, how do you trace it to understand exactly what's happening here? You can see the j here, j minus 1 here. Figure out exactly, what the logic is there. That's number 1. Number 2, given this piece of code, let's say without understanding the precise details or logic of this code, how do you derive the asymptotic upper bound and justify it? I think that one is even more important, right? I'll give you guys some exercises about tracing as well today, which you will get the opportunity to really try out paper tracing and also Eclipse debugger tracing. Right? I'll give you the more details a little bit later today. And this is the last page that we spoke about. And we basically just talk about sorting order. But just before that, guys, any question from last time? All right, sounds good. So I would suggest we just go back to the sorting order. I just want to finish the definition very quickly and then give you guys one exercise to think about together, okay? So the slides we are talking about is slide number 4, okay? So we talk about these are the different possible sorting orders you might be given as part of the computational problem you want to solve. So you want to be very careful about which one is given to you. And once a particular one is given to you, you have to know what's the mathematical meaning for that. So you got to implement your Java code accordingly. I'll give you some exercise to try out as well after we talk about selection sort and insertion sort. All right, let's go back to the definition quickly. So we managed to talk about two of the possible orders. So let's say decreasing, descending, that simply means the trend of the value is going to just go down strictly. All right. So if you got one element here at index I, the next element at index I plus 1, the trend should go strictly down. That's why it's called decreasing, right? So that's why we say this element here must be strictly larger than that one there. On the other hand, if we say increasing, ascending, so this element here, compare the one right to its right, should be less than, all right? That's what we talk about. These two are very easy to see, and you notice that it will allow no duplicates because it's only either this or that. You don't really have the equal sign over here. And let's now move on to, for example, non-descending. That'll be the third possibility. Think about the none over here is like a negation, logically. So you say, it is not the case that I got descending. And we know descending very well. That one there is simply AI larger than AI plus 1. Exactly, right? Which is not the case. And if you try to distribute the negation over greater than, we know pretty well it should be turn into smaller than or equal to. So this is the definition for non-descending. Non-descending simply means the trend can either go up or stay flat. Okay, so what do I mean? Something like this. So if I can just draw over here, sorry, just give me one moment. So the trend can either go up or it can simply stay flat. Let me just be consistent with my notes. Sorry for the delay. So let's see this. You can have either go up over here, or it can stay flat, or, sorry, it can stay flat, or it can go up again. Right? So that's kind of the trend for non-descending. As long as it's not strictly decreasing, then you're fine. So this is one scenario. For example, if you got AI, and then this one is AI plus 1, for example, and that one there, obviously, you have the smaller than. Right? It's going up. On the other hand, if you got another one, for example, I'll just call that A at I plus 1. I plus 2, sorry, the next one. Okay? And this one here, you can see that one, obviously, is just equals, right? That's exactly what less than or equal to would mean. And let's see one example. Example will be 1, 2, 2, 3, 4. All right, you can see, for example, this part over here is the part that's ascending, right? That's the part that's less than. And this is the part, for example, 2 and 2 is the part that's staying flat. So that's equals. Okay, very easy to see. The last one is very symmetric to how you can define non-descending. So now we just got non-ascending. I'm going to sketch a little bit so you guys will just get an idea. Non-ascending, for example, I say non-ascending. That simply means not the case ascending. And we know from before, ascending simply means we're going to go up. We're not going up, basically, right? So we're not the case, we got smaller than. Distributes, negation over less than, we got larger than or equal to. So that's the full definition for non-ascending. All right, so larger than or equal to. So I'll put this down, and then let's now visualize it very quickly, right? So that means you can either go down, as long as you're not going up, you're fine. You can either go down, or you can stay flat, like that, or you can go down again. All right? Of course, you can stay flat for as many elements as you like. Okay? So let's now just be complete. So for example, you got AI here, AI plus 1, and then let's say this is AI plus 2. Right? If you look at the relation, so this one is smaller than, sorry, beg your pardon. This one is larger than, right? Apparently, this element here is higher than this, so that should be larger than. And then this one, the second one, the flat one, is also equal to. Okay, let's see one example here. You can just say 4, 3, 2, 2, 1. Right? So this part over here, obviously, that will be the larger part, right? One example for larger. And this one here, 2 and 2, just flat, which is also possible. A final observation. In these two cases, we do not allow any duplicates. Apparently, this one here, you allow duplicates. Especially the duplicate must be consecutive. That will make it flat, right? So this will be duplicates. Possible. Also, this one, duplicates, also possible. All right, it's very important for you to know whenever you're given the like an English meaning, so the English term about the order that you're supposed to define your algorithm, they should know what that really means, right? Questions? I have a question for you. There we go. Here's a question. Let's say we got two sets, conceptually. Set number 1 contains all the arrays sorted in a non-descending order. Set number 2, all the arrays sorted in ascending order. We got two sets. You can feel free to give yourself some examples since we just learned about them. how do you formulate the relation between S1 and S2? Or there's no relation at all. That could be a possibility too. Okay? Yeah, I'll pick something from the back. There we go. Nathan.
Thanks. So I think that S2 is a subset of S1.
When you say subset, you really meant S2 is a subset of S1.
And not that, I would say not a proper subset.
You would say not a proper subset.
No, a proper subset.
Okay, you're saying that we should get rid of the equal sign.
No, I take that back. That was a mistake, sorry.
Okay, so final answer from you, S2 is a subset of S1.
Yes.
Okay, you cannot change anymore. Good. So now this is saying you allow the possibility where this and this can be equal. Okay, sure. Anyone else? How about you?
I mean, S2 is basically S1 without the duplicate elements.
Aha, so would you say it's also subset or something else?
It is subset.
Still subset? Maybe you guys are getting somewhere. I think what your fellow students say about allowing duplicates or not, that's definitely to the point. But to really formulate that using subset here may not be accurate enough. You may want to use this one instead. Okay? Good try. Thank you. What we're going to have is S2, a proper subset of S1. Specifically, let me now visualize it and tell you, whenever you say a set, yeah.
So what if like S1 doesn't have any duplicate elements?
Or remember, S1 actually contains all the non-descending, which definitely include those that contains a duplicate. We say all the possible, right? Yeah, don't forget the S1 and S2, we say all the possible, all. We're not talking about some specific example you're given, all right? Yeah, maybe that's what you're confused about. That's okay. All right, let's now visualize this, okay? So let's say we got, let me make it even better for you. Let's say this is S2, okay? S2, and let's say S1 over here, S1, all right? So what I would do is S2 is going to be a strictly smaller set. S1, sorry, not that green. There we go. That one there is the strictly larger set, all right? And this one here is S2. S2 is about the ascending. And for S1, it's about the non-descending. And if you claim that it's actually a proper subset, that means you must be able to find a member over here that is not a member of the strictly smaller set. That's what proper subset really means. You got at least one element there that's in the larger set but not in the smaller set. Right? That's exactly what proper subset. Give me one example there. How about go back to you? I'm pretty sure you know. Give me one example.
Yeah, like for S1, like 1, 2, 2, 3.
Yeah, exactly, right? 1, 2, 2, 3. Obviously, you can see that 1, 2, 2, 3 is non-descending because we allows either ascending or flat. However, is this array ascending? Not quite, because this part over here is not ascending. So that's why this one should not belong to here. All right, so take this exercise here to really help you check your understanding, right? So this one here is not ascending. That's why this array here should not be a member of that, all right? Whenever you want to determine between proper subset versus subset, you want to make sure you understand why I would choose this one instead, because I can definitely find some witness, at least one. I can easily find that, okay? All right, question about this. All right, that's good. All right, let's now move on. Okay, so we are now done with just clarifying about the terminology, about the sorting order. And let's now consider over here, the last bullet point here. We want to consider two alternative implementation strategies, namely selection sort and insertion sort. They're given the same problem, which is to take one input and I want to return the output that's going to sort the input in non-descending order, right? You guys know non-descending, what that really means very well, all right? That's the problem, input and output. So I'm going to do selection sort and insertion sort. And so here's a lesson I'm going to show you right away. In order to really derive the running time for an algorithm, you don't really need to get a piece of code first. You don't even need to open your Eclipse or even write any code on the paper. All you got to do is somehow sketch, kind of visually sketch the critical steps of your algorithm, and you will be able to derive. That's something I want to show to you. The Java code itself is not that critical. Of course, you got to study that. I'll rely on you on that. But I'm going to show you more about the critical steps that's going to be visualized for selection sort and insertion sort. Okay, that's what we're going to do. If you go to the next slides over here, let's now talk about selection sort. So these 2 bullet points basically summarize the essence about selection sort. Okay, I'll read it first, and then we'll follow that kind of principle and do one example, and then I'm going to generalize from there to give you the running time. We'll derive it together. We don't even see the Java code, not yet. Okay. So what you want to do is you want to maintain something called the sorted portion of an array. Think about your array is initially unsorted. So the sorted portion initially just empty. Eventually, once your sorting algorithm is terminated, the sorting portion should cover the entire array. That's the principle. Right? And then we're going to go from left to right in the array. And then the selection sort, well, it gets its name just because the critical thing you got to do every time is to keep selecting something. We're going to keep selecting the minimum value from the unsorted portion. Once we select the minimum, we're going to grow the sorted portion by 1 element, being that minimum we just selected. All right, so that's kind of the step we're going to follow through iteratively. We don't talk about recursion, iteratively. Okay. Let's now visualize about selection sort, and I would suggest it. Of course, I'm trying to make the visual as much. One moment, sorry. That's not mine, actually. Somebody left. Can you do me a favor? Can you try to turn it off, please? Yeah, thank you. Oh, is it yours? Okay. Somebody found it there. Okay. That's good. Yeah, please. Yeah, thank you. All right, sorry for the interruption here. Yeah. So now let's talk about selection sort. So as I try to visually illustrate about the different steps for this particular example, it should be rather easy, right? We only got 4 elements in the array. I mean, how many iterations it's going to take? Not that many. So we're going to take a look at that and see exactly that can be done. At the same time, you may want to think to yourself, how efficient is that in general? Let's say the array is very big, size n. Okay. Let's now talk about that one. So this is what's given, right? The convention is I use the red to signal which part of the array is unsorted. And then as we try to get more and more sorting done, you will see that array, you'll get bigger and bigger parts becoming green, right? That's what you will see, right? And red for unsorted and green for sorted, okay? Now let's follow that. The first step will go like this. We're going to select the minimum. Okay, I'll put it here. We're going to select the minimum from the entire array in the beginning, from index 0 to index 3. Index 0 to index 3, the entire array. The minimum here, for sure, is going to be A1, right? That's something we're going to do. So select it, select that one there. And then what's going to happen is we're going to, oh, by the way, when I show you that, you don't think that I'm creating different array. I'm using the same array, but just showing you different step, okay? Okay, I'm just going to show you what's going to happen in the next step, right? You will see exactly what's going to happen. Okay, this guy here. So the sorted portion is going to grow from left to right. Okay, from left to right. So now I want to somehow insert this guy here into the sorted portion, right? I can do that very efficiently. All I do is I can simply just maybe swap these 2 elements, right? Just swap these 2, right? 1 and 3, okay? So what I will do is I'm going to get 1 and 3, and the rest remain the same. So what's going to happen is this part over here is the sorted portion. And this part over here is the unsorted portion. one thing very important to note visually. Every time you try to make some progress on your selection sort, you're growing the sorted portion by just one element. And you're shrinking the unsorted portion by exactly one element. All right? That's a critical thing. And because you're selecting the minimum, by the way, you're selecting the minimum from there. So every time you want to put the minimum, for example, here to the sorted portion, you just append it to the end of the sorted portion. Just append to the end. So that's an efficient operation. We'll see one more. Okay? And now let's do the next step. The next step will be we want to now select the minimum again. So you want to select the minimum. Okay, you know what? Let me just be careful because I do have a few steps. I want to make sure I got enough space. Give me one moment. Okay, I'll make it a little bit like that. I want to be precautionary over here. All right, the next step. We're going to select the minimum, which will be this right here. Agree? That's a minimum, right? In the red area. So that one there, which I'm going to put here. Select the minimum from A1 to A3. And once we have done that, the idea will be this is guaranteed to be the minimum, or overall the second minimum, if you see what I mean, right? This is guaranteed to be the minimum. So all we got to do is we want to append that to the end of the sorted portion so we can grow it by one. How do we append it? That's not expensive. You don't need to shift anything. All you got to do is swap these two elements. Swap is easy, right? You know how to swap, right? So all we got to do is we're going to now swap these two. Swap this one and this one here, right? I'll just put some arrow here so you will see. All right, let's now try to put another one here. So that one there is going to be just another array over here. What's going to happen is, since we're going to swap 2 and 3, so that's going to be 1 and 2. And then 4 and 3, agree? 3 is just swap to the end. So 1, 2, 4, 3. 1, 2, 4, and 3. So effectively, the sorted portion is going to be grown by another one, which will be over here. The unsorted portion is just going to be here. All right? You kind of see the idea, but let's do a few more. Just make sure it's complete. Because once I complete all the steps, I can generalize it and tell you what the running time is. Okay? Let's do another step. All right, so that one there, I'm just going to select again. Just keep selecting. Basically, keep selecting. That's why it's called selection sort. I'm going to select between A2 and A3, right? So you can see the area from which I got to select is getting smaller and smaller. What does that mean? The selection is the most expensive when you start the first step. You're just getting cheaper and cheaper until the end. Interesting observation. Okay? So here, you're going to see that I got 2 here. Okay, I'm going to write it down. So you're going to select the minimum from A2 to A3. All right? And the minimum, of course, is this guy here. And then we're going to conceptually append this guy here to the end of the sorted portion so it can grow by 1. But just do swap. We're going to swap these two, right? Of course, there are certain implementation I'm kind of leaving out over here. Exactly how do you swap? And also swap from where to where. That's something you will see the Java code. That's something you got to do the tracing on your own, which will be some exercise for you. All right. So let's swap, and then I'm just going to get another array over here. We're getting very close. Okay. So I still got 1 and 2 over here, and I swap. So I got 1, 2, 3, 4. All right. The unsorted portion is now reduced to only size 1. And the sorted portion is now 1, 2, 3. Okay? Strictly speaking, we are not done yet, even though the array is already sorted. So let's, to make it a little bit easier for us to observe the pattern, let's do one more step, right? Which will be cheap. The last step that we're going to do will be we just have to select the minimum once more. Select the minimum from basically A3 to A3. From A3 to A3, it's basically a portion of size 1, right? Just select it. And once you have selected that, you want to append it to the end of the portion. Well, you can think about swap with itself, conceptually, right? Something like that. So what you will get is you're going to get the final outcome over here. And that one there is going to be 1, 2, 3, 4, with the entire region of the array being sorted. Oh, there we go. That's selection sort. Conceptually, you got to understand. I think that this one might just give you enough intuition. All right? Guys, based on this, can anybody kind of guess what the running time should be? If I got input of size n, and then I want to use selection sort. In some way, it looks like a linear, because the number of steps I need to really apply over here should be corresponding to how large the sorted portion should be ultimately. Because I know ultimately I want to build a sorted portion of size, for example, 4. So that means I need 1, 2, 3, 4, 4 steps. Looks like linear. Or I'm misleading you. Okay. Yeah, go ahead.
It's n squared.
N squared? So why not linear? Where does that extra times n comes from?
Okay, so first of all, we're gonna have to figure out like where exactly in our array that minimum value is.
Mm-hmm.
And that operation in and of itself is gonna take n times.
Yep.
Because we're gonna have to iterate through the entire array to figure out what the minimum value is. Now that we found the minimum value,
Mm-hmm.
now we're gonna have to take that and put it in the correct spot, and then
Yep.
search again. And that entire operation, like where we're searching, putting in the right spot, searching, putting in the right spot, the number of times that happens is also n. So
Yeah.
if we're taking n time to find the number, and then we need to do that step n number of times, that is an n squared algorithm.
Yep, thank you. That's pretty much it. But let me summarize. Okay. Basically, number one, we know that there are, basically you can see some nested loop structure already somehow, okay, conceptually. Number one, you need a first layer, first dimension. You got n different steps over here. For each step, you got to select the minimum. As I said earlier, the first selection will be the most expensive. It's going to search the minimum for the entire array, like a find max, which will be n. The second one here is going to be slightly cheaper, n minus 1. The third one there will be n minus 2, all the way to just 1. And this should be something that looks familiar to you, right? So you can see somehow we have to take this one into consideration as well, right? That's conceptually what you got to think it through, right? It's not just linear. Linear is just about the number of steps you need, but each step itself may not be constant. That's the main point. Right, I'm going to generalize this, and then we'll figure that out. Okay, exactly. So think about, I'm going to draw again. In general, let's say, okay, I'm just going to get rid of these two. You kind of remember the convention, red for unsorted and green for sorted. Okay, let's now generalize it. If I got an array of size n, I'll put n here, not for the element content, just for the size. All right. In the beginning, I simply got everything unsorted. That's what I got. All right. When I apply the very first step, so there are two parts, basically. Number one is I want to select the minimum. I'll just say min. I want to select the minimum. I want to select the minimum out of n elements. It's going to be linear, like a find max. And also, I need to append that selected minimum to the end of the sorted portion, which I can easily do some swap. So I'll just say append. That one there is just 1. All right. And then once I finish the first step, I basically got the same array of the same size, except I'm going to have the sorted portion looks like this, right? I'm going to put 1 here. Just say we got 1 element there. All right. On the other hand, we got n minus 1 elements in the unsorted portion, right? That will be n minus 1. All right. Let's do one more step before we say dot, dot, dot. What will be the next step, right? For the next step, we're going to do something very similar. we got to select the minimum from the unsorted portion. But now the unsorted portion has shrunk by one element already from the previous iteration. So now it should be minimum routine should be, rather than n, should be n minus 1. But the append will still be a swap, still 1. All right. So to select the minimum, it's going to be n minus 1. And for the append, it's actually going to be still 1, just involves swap. All right, let me just make sure I draw this, and then we can imagine what's going to happen in the very last step. So this will be a little bit bigger. I'm just going to put 2 here, meaning that there are 2 elements here, right? That's sorted. And here it should be n minus 2. So n 2 here, and also n minus 2 over here. All right, let's now do dot 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 so we can generalize it. What we're going to do is we're going to see what's going to happen in the very, very last step. The very last step will go like this. The very last step is actually going to be executed such that the resulting array is going to be completely sorted, right? So that one there is actually going to be n elements here, right? Completely sorted. But what will be the layout for its input for the last step, right? Well, it's going to be just like this one here. We got just one element left in the unsorted portion, right? So I'm just going to get this part here, and then I'm going to get this part here, okay? So this is going to be just 1, and then n minus 1. So the last one here, so dot dot dot. To choose the minimum, it will just be 1. I just choose one element from the unsorted portion of one element. And then I also got the append, which will be just swap like that. What we're going to sum up with will be the selection process will be n plus n minus 1 all the way to 1. We know what it is. It's a arithmetic sequence with fixed constant minus 1, right? And then we also got the append, which is just 1 for every iteration, right? And we want to see how many steps there are. If you see the pattern here, you can see we go from n all the way down to 1. So basically from 1 to n, how many integers are there? N, right? N steps. You can see so far we have not even talked about coding. It's not necessary, right? It's just not necessary, okay? So now let's summarize it as follows. Big O over here. And then, first of all, let's talk about append, which is the easy one. It's going to be n times 1. So n will be the number of steps necessary. And the 1 here will be just a swap operation that we need, okay? And then what about the selection process for each one of them, right? And we know that that one there is going to be n plus n minus 1, n plus n minus 1 plus all the way to 1. Sorry, I'm just running out of space, but you can see what I'm doing here, right? It's a arithmetic sequence over there. And that's selecting the minimum. And let me just make one more annotation for you. Think about this is the first selection. And this one here is the last selection. All right. So let's now take a look. This will be equal to this one here, just n. And this one here, we learned from last time, it will be n squared, right? Asymptotically. So I'll put n squared here. And this is higher, it's going to dominate, so n squared. Okay, let me also get rid of this. We don't need that anymore. So the ultimate result for selection sort is big O of n squared. It's a quadratic algorithm. For not so large input array, it's acceptable. But we're going to see something more efficient later in the course. All right, guys, any question? We good? All right. Okay, I'll put it here. All right, that's about selection sort. And let's talk about the other one, which is called insertion sort. Well, from its name, it tells you the main routine you're going to keep doing is inserting rather than selecting, all right? And you also want to somehow, the reason that we kind of study these two algorithms together because they kind of work in a very similar way. When we said earlier, the first selection is the most expensive one. But in the insertion sort, the first insertion is the cheapest one. And you will just get more and more expensive. That's the kind of symmetry part, right? You're going to see, right? But of course, you don't memorize these facts. You just got to be able to visualize, again, using some small example and derive all the properties. Let's take a look. All right, insertion sort. Okay, we use the same array over here. And then let's see exactly how to understand it. And the way we're going to generalize it, rather than join, let me just go over the example still visually. I think that's important for you. That will also help you to understand the tracing part. But once we get to the generalization part, I'm just going to give you a different way of presenting, right? You can see which one suits you better. Again, you guys know the color convention, right? So I'm going to delete that just to give me more space. We got this initial array. And for the insertion sort, we're doing we try to do one iteration less, okay? Just conceptually, okay? Again, we got sorted portion initially just 1 rather than 0. I mean length 1 rather than length 0. So let's say initially we got this very first element is considered as the sorted portion. That's a subarray with just one element 3, and that one there is sorted, okay? And this is the part that's unsorted, okay? Let's now see how we can do it. Insertion sort also involves something called selection, but don't get confused. The selection here is very easy. You're not selecting minimum or maximum. All you select will be the leftmost elements in the unsorted portion. All right, I'll write it down. Oh, actually, that's here. The first element from the unsorted portion. And this one here is a very cheap operation. Just for this guy here itself, I can tell you that it's just big of 1. You just got to know which index it is selected. Okay, no loop is involved for this selection. Once you have selected this guy here, you're actually going to say, this is the element I have selected. And this is the array that's already sorted. How can I insert this element into this array, in this case, either to the left or to the right, to make the new array of size 2 still sorted? All right, I'll repeat this maybe in a different, maybe a number of times so you will see. Okay, so let's now say that. So the first step, we're just going to say we want to insert element at index 1. That's what we're going to do. Right? You can think about here, if I want to insert 1 into this array, there are two possibilities. I can either insert 1 before 3, or I can insert 1 after 3. Obviously, I should really insert it before 3. So that'd be 1, 3, rather than 3, 1. 1, 3 is the sorted order I want, right? All right, let's now try to put that array down, and then we'll move on to a few more steps so you will get a little bit more intuition. Okay. So that one there, I'm just going to insert. So after the insertion, 1 is going to be inserted to the left of 3. And 3 remains to be there, right? Just somehow get shifted, all right? And then 4 and 2 remain there. So what we have done, this part here is similar to selection sort. We have grown the size of the sorted portion by 1. We have shrunk the unsorted portion by 1 as well at the same time. All right, 1, 3. All right, one more step. The next step is going to follow something very similar. Again, we want to select very cheaply the leftmost element in the unsorted portion, just 4. All right, so I'm going to circle that. That's something I'm going to select. So I'm going to insert that particular selected element, which would be A2. So now, let's now think about it, right? So now it's the sorted portion is large enough for us to make a little bit discussion here. In general, let's not even think about the element type, the element here, okay? I got an array that's already sorted of size 2. I want to insert a new element into the array. There are 3 possibilities, agree? I can either insert a new element as the first one. I can insert the new element as the middle one. Or I can insert the element into the third one, right? I got 1 here, I got 2 here, I got 3 here. Which one will be more expensive? 1, 2, or 3? You may want to think about the insertion itself may not be so bad. It's really about the consequence of doing that, because you want to make sure the inserted array remains sorted. So not just the new element got to be there, but also the rest of the elements should still remain sorted. 1, 2, or 3, which one is more expensive? All right. 1? Okay, 1. I'll tell you the reason. I'm pretty sure you guys know. All right. 1 will turn out to be the more expensive one, because if I try to insert this one to here, that means this will be index 0. This one should be index 1. This one should be index 2. In that way, I'm shifting the entire block to the right by 1 position, which is something we saw last time. Remember? Okay, I'm going to visualize this step a little bit more generally in a moment. Right? For now, I want to give you just some repetition. All right. So now, if I want to insert maybe 4 into here, here is not the most expensive case. So you just got to go 1, 3, and 4 afterwards, right? Which is okay. It really depends on the input. So I'm just going to put this array over here. Again, I'm going to get 1, 3, and 4. All right? So that is the new sorted portion over here. And then I got 2 here. Okay? That remains the same. Like that. All right. We got one more step. Okay. If you like, I can just give you, this will be the last step. And for the last step, you can make a little bit of generalization. Think about over here. This will be the starting point for the last step. The size of sorted portion is exactly n minus 1, right? Because now in this case, the array size is 4. 4 minus 1 would be 3. So we got exactly 3 elements here, right? We got just 1 element left. Okay? It's a very important thing to actually point it out right here. And how do we continue? So one last step. So you got to select this guy here, right? That's kind of leftmost for the unsorted portion. So you want to insert A3. Right, here we know pretty well, so it should not be inserted in the beginning. It should just be inserted right between 1 and 3 to make it sorted. Okay? The actual algorithm is going to figure out exactly how to do it. But to really derive the running time, we don't need to. We all need to know what's the worst case about insertion, which I'll speak about when I generalize it. All right, so let's now put it here. All right. And then after insertion, 1 here, 2 here, 3 here, 4 here. So that's the final outcome over here. All right? If you look at the color trend, it's really similar to the selection sort, basically, right? Similar in that we start with all red or mostly red until we got all green, right? That's a similar trend. But the way each individual step works is a bit different. You got to watch out the details. Okay? Before we generalize the running time, I want to mention one more visual, and then we can talk about it. Okay? Let's talk about insertion. Worst case. So worst case for insertion, individual insertion. Okay, let's say this. If I got an array like this, let's say I'm somewhere in the middle of the algorithm, somewhere, okay? So the setup goes like this. I have, let's say, right here, okay? Okay, I think I might need this again, so let me just copy that. Okay, good. So this is set up. Let's say this part over here is unsorted, all right? And this part here is sorted. That's what we have, right? And then if I want to apply the next step, that means I got to insert. If I want to insert, what's going to happen is I'm basically going to choose. So let me just do a little bit more extra here. I'm just going to make some line over here. So you can see that element there is very special. That's the leftmost element we're going to choose directly. Okay? So we choose that element there, and then we're going to somehow insert it into the sorted portion. And we talk about the worst case. The worst case goes like this. Okay? It's going to be basically that element there should be somehow moved to the leftmost part of the sorted portion. Whereas, if you think about, let me just put one more here. Okay, let me just finish the coloring and then I'll explain that. It'll be easier. All right, so this will be the new sorted portion with exactly one more element, and it is important for you to see the following, okay, like that. And let me say here, look at this part here. This is the old sorted portion. That one there basically has been shifted entirely to the right because I'm inserting the new element to the leftmost in the sorted portion. Right? That shift operation is going to involve a loop that's going to run up to n in the worst case. All right? So that's something you want to review about the insert example that we did last time. Okay? Let me recap very quickly and then we'll move on. Okay? So this generalized a single insertion step. Okay, so we go from here to here. You can see, first of all, the sorted portion has grown from here to here by one element. Accordingly, the unsorted portion shrunk by one element, right? Number one. Number two, the one you chose over here to insert into the sorted portion happened to be the minimum in the new sorted portion. That means once you get it there, all the rest should be shifted to the right by one position, which is going to be big of n in the worst case, right? That's why I said this will be the worst case for insertion. And now, since we are talking about asymptotic upper bound, so when we generalize the running time, think about every insert is the worst case. We're always inserting into the leftmost of the sorted portion, just easier for us to think about, all right? So this is a very important insight for you to know, and then I'm now going to generalize the running time for insertion sort using a table. Okay, that's just another way to present the outcome. So you can choose which one you like. Either you can try to maybe draw, like what I did earlier, or you can choose a table, right? You can, whatever you like. Right, let's now try to summarize, and then we'll calculate the running time. So the table I'm going to do is I'm going to have here. I'm going to have something called a step. Also, I have what to choose, like what to select, basically. Okay, and then also it is important to know what's the size of the sorted portion, because the size of the sorted portion is going to determine the running time for the worst case insert. So that's why I also need to record that. All right. And then accordingly, I will know what's the maximum cost for that particular insert. I'm considering the max. The maximum cost for the insert. All right, I'm just going to use this table here to summarize the generalize about the running time. All right, let's look at that row by row. Right? We just need maybe a few rows before we can say dot, dot, dot. Step number one. We basically choose just A1, right? And we start with the sorted portion being just one element, right? We don't start with empty, right? Just remember that. So here, the size will be just one. Accordingly, what's the maximum cost? Just one, depending on the size, right? Just make it a little bit easier. All right, let's do a few, maybe a couple more rows. The second step, think about after the first step is applied when the sorted portion is already of size 1. The second step is going to apply when the sorted portion is already size 2, etc. All right? And then the second one there, we're going to choose something. Okay? Just A2, actually not something. Right? You can see we choose A1, A2, A3, etc. It's got to be that order always because there's no minimum maximum we're choosing. And the size of the sorted portion in the second step will just be 2, right? Accordingly, the maximum cost will be 2. One more, and then we'll generalize. And then a 3 over here, size 3, and then maximum cost is 3, right? Dot, dot, dot. What will be the last step number? Here is the thing. Anybody? Remember, the step number corresponds to how large the sorted portion is right now before we apply the current step. This will be the last step, right? For this last step over here, what is the size of the sorted portion? N minus 1. Right? That's why I mentioned that earlier. All right, guys, you really want to pay attention to those details as well, right? All right, N minus 1 will be the last one. For that, for which we choose AN minus 1. And interestingly, N minus 1 is a valid index, right? It's the last valid index, maximum valid index possible, right? That also nicely corresponds to what we're choosing. We're choosing last element here. All right, so that one there is going to be size for the sorted portion should be exactly N minus 1, right? N minus 1 here. And then the cost will be N minus 1. Okay, dot, 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 dot. And for the insert over here, if you want, okay, so here, 1, 2, 3, all the way to N minus 1. Again, we got arithmetic sequence, except it's now from 1 all the way to N minus 1, as opposed to N all the way to 1. You can see the symmetry here, right, between the two sorting algorithms, right? That's also the detail you want to pay attention to. All right, so let's now do the final summation of all the things together, all right? So everything together is going to be big O over here. First of all, we know that there are N minus 1 step. Let me write it down here. From 1 to N minus 1, N minus 1 steps. So I'm going to say, first of all, N minus 1 steps. For each step, I got to choose the leftmost element, just 1. So that one there multiplied by 1. So just remember this is choosing the first unsorted item, right? Plus this part over here about insert, which we did some nice work about enumerating them, right? So that one there is going to be basically 1 plus 2 plus 3 plus all the way to N minus 1. And this part here is just arithmetic sequence. We know that it's N squared, right? So we got equals big O of here N minus 1, just N basically, okay? N plus N squared, and you can see that this one here, highest power, is going to dominate. N squared, ultimately. So that's the final outcome. Again, let me emphasize one more time. Have we seen any Java code yet? No. That's really the best value you can get from today's class. For you to design an algorithm, you don't need to write code to begin with. And you can figure out the running time quite nicely. Alrighty. Okay, so I got about 20 minutes. I would suggest I just want to talk about the Java code very quickly, about 5 minutes, and then we'll take a short break. All right? Selection sort, insertion sort. Very good. Okay. Selection sort. Okay, actually, you know what? Let me just say one more thing. Okay, here. Okay, let's now see some Java code, right? We have done all the good work. Let's now see some Java code. So let me say this is the selection sort, Java code. I also gave you the Java source code. You don't need to type. It's there for a reason, okay? Let's say we do one exercise very quickly, okay? Now, let's say you don't understand exactly how this nested loop works for selection sort. Somehow correspond to what I just visualized to you. Can you derive the asymptotic upper bound just from this piece of code? I can easily just say, I don't even tell you it's selection sort, right? How can you derive the running time? All right? Stare at that just for 30 seconds. And then we'll do it together quickly. Wouldn't take long. Because that one there is very similar to something we did earlier, last time. All right? Take a guess. Well, actually, selection is so, right? Should be n squared. Sorry, it's a dumb question. Sorry, should be n squared. But now we got to see exactly how that can be run into n squared. Question.
Oh, it's not a question. It's an answer.
Answer n squared, right?
Yeah, it's n squared, but in particular, it's going to form a triangle.
Yeah, the triangle. Thank you for mentioning that. So you're going to see that triangle shape. Let's see that very quickly, right? We don't need to spend too much time, but it's good to just give you the idea. So to start with, the n here, again, it will be a the length. Right? I might go a little bit faster here because we have done that, but let's just follow that. Let's now try to look at the body of the code. If you look at this part over here, line number 2, and also line number from 6 to 8, this will be constant time, right? Just assignment. All these are the swap. Okay, you will see that later when you trace. And this part over here, the number of is going to be executed for the number of time corresponding to the value of I, basically. Okay, it's going to be executed according to values of I, the outer loop. On the other hand, you will see another one here, which I'm going to do in blue. Okay, this one here in line number 5. This one here is right in the body of the inner loop, right? You can see some indentation there also to kind of signal to you. So this one will be executed according to the values of ij combination. And that line alone, line number 5, is also 1. Agree? Okay? Primitive operation. And we're just going to figure out the patterns for I and j. So let's say I use purple for I, and also I use green for j. All right? And let's enumerate the pattern very quickly, right? Just a few minutes. So if you try that, you're going to see that I here is going to be from 0 all the way to n minus 2, right? You're going to say 0, 1, 2, all the way to n minus 2. How many values, how many iterations are there? Precisely. We're talking about from 0 to n minus 2. What would that be? N minus 2 minus 0 plus 1. What should be? Thank you. Thank you so much. Okay, n minus 1 iterations. All right, that's important, right? You can see we're kind of putting everything together, right? N minus 1 iteration. That's good. And let's see for each I, what will be the value for j? Quickly. All right. Let's say for the j here, it's going to be from I all the way to n minus 1, right? It's going to be from, for example, 0, 1, 2, all the way to n minus 1. And then 1, 2, all the way to n minus 1. And 2, all the way to n minus 1. What about the last row? What should I put? How many? Yeah, go ahead. Yeah, please. No, from n minus 2. Remember, yeah, that's why I'm asking. You can see n minus 2, right? That's a starting point. That's the value for I, so j should start from that. All right? So it will be n minus 2 and then n minus 1. So this is almost like a triangle, except you cut off that corner, right? Almost like. So that's why when we talk about calculating the area, so may not be exactly, right? So I think, yeah, this one may give you some example. All right, so this is a nice triangle, almost triangle shape, almost. All right, like that. All right. So now that one there, we just got to count. So let's say here. Let's see here. This. How many are here? From 0 to n minus 1, n. From 1 to n minus 1, n minus 1. From 2 to n minus 1, we got n minus 2. All the way to n minus 2 to n minus 1, 2. All right. Now we are ready to sum them up. All right. It's now going to be big O of, okay, first of all, we know that we got n minus 1 iterations. So I'm going to put n minus 1 over here times 1. Right? I'm going to annotate here. N minus 1 is just about the number of iterations of the outer loop. And the 1 here is really line number 3 and line number 6 to line number 8. And then plus the difficult part here, right? Each one is going to be 1, but how many have we got? We're going to add up this sequence here, which is arithmetic. So we're going to get basically here, first of all, let me see, n plus n minus 1 plus all the way to 2. All right? And then that one there multiplied by just 1. So the 1 here is really line number 5. All right? Line number 5. Line number 5. And this part over here is about the number of ij combinations. And this one here, if you want to put it aside, okay, I'll just put it aside. That'll be, according to our formula, it's going to be the beginning plus the end, 2, multiplied by the number of turns over here, right? You can see we basically go from n to down to 2. Should be n minus 1, right? N minus 1 divided by 2. And that one there, basically n squared is going to dominate everything else, n squared, all right? This one here is just n squared, okay? So let's now do a little bit of simplification here. Big O of, so I got n minus 1 plus n squared. Obviously, this one here is going to dominate. Big O of n squared. So this one is telling you, well, in the previous example we said, you can derive the asymptotic upper bound without seeing the code. And here we're saying you can derive the asymptotic upper bound without knowing the logic of the code, right? Good. Okay, give me 1 minute, and maybe 1 or 2 minutes, and then I'll let you take a break, okay? The insertion store Java code is also given to you, and you got to derive the asymptotic upper bound as exercise, okay? Give it a try. Exercise for you. And then, now, let me go over some slide with you, and I'm going to keep the next 2 pages completely clean. Okay, and then I'll tell you what to do. Okay. So that's the selection sort, and we've gone through all the details. And for the insertion sort, I think once you're done with that, like asymptotic upper bound exercise I just mentioned to you, you can check the answer at the end. Right? Okay, I'm going to skip that quickly. Okay. Now, let's see the exercise I'm going to assign to you. So given a fragment of Java code, you're expected to, in general, for this course, number 1, derive the asymptotic upper bound, for sure. Okay. Number 2, to trace the runtime execution is also very important. We did 1 already. Okay. Number 2 is going to actually be up to you. Okay. So what's going to happen is you will now be expected to really take selection sort over here and trace it exactly how things are going to work. Only doing that will actually give you totally appreciate what's happening here. All right, I already helped you about the variables you should really keep track of. All right, over here, you can do the rest. So that's the input array. Okay, and you're going to do something similar for the insertion sort. But if you want to go over a solution, you can reach out to me. But I do have some nice videos recorded here that will walk you through the entire process. Okay, so these 2 will be about filling out a tracing table. Follow them. If you got any question, you can let me know. And the third one here is also very important. That one is about tracing on Eclipse. So that video also shows you how you can set up the breakpoint and see from the debugger how these 2 algorithms will work. Maybe some of them, you'll get an idea. All right, so this slide here, very important exercises. If I may tell you, I'm going to ask you some questions at some point. Not in the programming test, but in the written test or the exam. So please do this exercise. It's good for your learning. Okay. And then one more thing, and then I'll take a short break. So if we, so far we have seen the 2 sorting algorithm. So asymptotically, they will just be quadratic. Later on, we're going to see 3 more sorting algorithms: merge sort, quick sort, and heap sort. They will take n log n, which is strictly more efficient. All right, we'll see that. Okay, just a heads up. All right, so this will be the final thing I want to mention before we take a short break. So this will be more exercise for you. But basically, what I want you to do is this. You want to take the insertion sort and selection sort, choose one. How about that? Choose one, at least do one. Choose a Java code, which is already made available to you. Make the following modification. Two things, okay, which is mentioned in the slide. Thing number one, we are actually going to the sorted portion. Rather than maintain the sorted portion on the left, I want it to be on the right. As you can see, every time we still grow the sorted portion, but you can see it's from the right over here. All right. Number two, let's say we change the sorting order. The one we did earlier is about non-descending. How about non-ascending? For example, let's say finally you might just get something like a 5, 4, 3, 3. Okay. You want to take the Java code, either selection sort, insertion sort, choose one, and make the modification so that we got these two new criteria satisfied. That will be your exercise. Should not be too difficult to do. All right. All right. Any question, please? All right. You can also see the slide. That's exactly what I just mentioned. So just save time by visualizing it. All right. Okay, why don't we take a 2 minutes break? I think we will get about 5 minutes or so just to have some very quick introduction to linked lists. All right, please get your iClicker and we'll take attendance. All right, so before the break, we cover the selection sort, insertion sort from different angles. Please review the materials over the weekend so you will be ready for just maybe other challenges. So we're going to move on to a very, very important topic about linked list, right? Today we only got about 5 minutes, so I'm going to start something a little bit more like a general introduction. So we're going to cover two types of linked list. One will be singly linked, the other one will be doubly linked. We hopefully will need about 3 to 4 lectures to cover the entire thing. I want to go steadily, but after Tuesday's lecture, you will be ready to do assignment number 2 for sure, because there's an unbounded number of linked list problems out there. We're going to cover something very basic to show you the tracing scale, the principle. It should be enough for you to really work on other problems on your own. So that'll be the idea. All right, so let me do as much as I can. So let me now do some quick introduction. Just mention some critical terms, and then we revisit them very often as we go for other example. All right. So what we'll start with is something called singly linked list. Okay, over here. All right, over here. And the first concept will be, it's basically a chain of connected nodes using reference aliasing, which you guys should know from 2030 what aliasing is. All right, so let's now visualize what's really happening over here. Okay, at least you can do something today. A chain of connected nodes. Node, let's start with the notion about node. So this is really a node over here, like objects. So this is a node. And each node has, for singly linked list, each node has 2 attributes or 2 parts. One part is called the data, because after all, you got to store some data. So there will be a link over here called data. And in order to make it more like a chain, you have to somehow got another one here that's called next. Right? So just remember each node has 2 attributes, data and also next. Very important. All right. And then let's now see how we can play with it quickly. How can I somehow create a chain of nodes? There will be many objects of type node in the runtime. If I just get another object over here, for example, right here, what does this mean? That means I got 2 nodes in the chain. This is the first node. The next node of that is this particular node. And the next node of that is pointing to nothing. Let me do one more. And then I will do a little bit more, make it a little bit more precise for you. And we can also store some data. Let's say we're storing string, just to make it easy. So maybe we will get, let's say the first data is Alan. And the second data over here is called Mark. And the next one is called Tom. All right. And let's say for referencing, let's say this guy here, we call it N. N was declared to be of type node. Let's now play with this structure already to see what's going to happen. You can think about N here is the first node in the chain. And then I can say N.data. That one there is just the Allen objects. Right? You can see N here, and then follow data, you got Allen. Also, I can say N.next. Obviously, and which you refer to this node here, .next is referring to another node. Right? First of all, I know that N.next is not equal to null. It's something there. And I can say N.next dot data. What is that? Mark. All right? Okay, let's move on. So now we got N here, and then we got N.next over here. All right, let's continue. Okay, I can also say N.next .next. That's also not equal to null. N is here, .next is this node here, right? And then if I say N.next data, so that will be equal to Tom. Okay, one more as exercise, and then we're done. What if I say N.next dot data? This will be the final one for today. It compiles, it will run. Anybody? No? You're getting somewhere, but it's not exactly null, I'm afraid. It's actually much worse than null. And over here, next, this node, next, this node, next should be null. .data, null pointer exception. This would be your best friend in your assignment and programming test. You'll run into such thing very often. So you want to avoid your best friend for this linked list. All right? So I'm going to write it down, null pointer exception. Thank you so much. I'll see you next week.